Hello, Calculus 2. Okay, so there's a surprise quiz. Hopefully you've seen that. So the question is at the top, and there's just a place down here to give me something. If you're on campus, you can just give me a piece of paper. That's totally cool. You don't have to upload anything. So I give you two functions, y equals x squared plus 1 and 3x minus 2y equals -4. They enclose a region. So you need to identify that enclosed region, and then you're going to rotate that region around the x-axis to generate a 3D shape. And I want the volume of that shape. What you need to give me, along with the volume, is some pretty pictures. So for sure, you're going to draw me a 2D picture showing me that enclosed region, showing me the axis you're rotating about, and labeling any other pieces you need to set up your disks or your shells. You get to choose. It's up to you. Disks or shells. I also want you to do an attempt at a 3D sketch. Okay? I'm not expecting much there. All right? So if you show me something that has some circles and lines in it, I'm going to call it close enough. That's not really what I'm testing you on. I just want you to give that a shot. What I'm testing you on is, can you draw the basic picture? Can you label that picture properly to set up the integral? And then can you evaluate the integral? This integral is doable without an integral calculator. You can do everything by hand on this one right here. But I highly recommend you check your work with any tools you want. All right, that's totally cool. And then one of your classmates was kind enough to post a 3D rendering from a computer. Let's check this out. I'm excited to see this. This is a 3D interactive rendering of the thing we're creating.
It takes a second to load.
Okay. So this is I guess a glass version of it, and I'm not quite sure how to work this tool. Ooh. Am I upside down now? Whoa. Sorry. It seems to be going backwards from what I'm telling the mouse to do. So you can see it's conical from one view, but it's got a curved interior. Yeah. Ooh, look at that. That is just sexy. What is, do you know what this is?
It's,
neither of those sounds familiar.
no, it's whatever she uses for the CAD class, which is
She just told me the name of it.
free. It starts with an F.
Is it? Oh, it's probably right there. What are you? You are A360.
Yeah. No, that sounds right. A360. Yeah.
A360? Okay.
Yep.
That's pretty cool. And there's a trial version, but then you got to learn how to use the software.
You can get it for free from the college. Sure.
Okay. Cool.
Students can.
All right. So.
And then there's an actual picture. You scroll down on the 12th a little bit.
Oh, check that out. A nice 2D rendering of the 3D object with the Z, X, and Y coordinates.
Red is X.
X, blue is Y.
Green is Y.
Green is Y.
Green is Y.
And Z is coming out?
Yeah.
Oh, yes, right. Of course it is. Yeah, because we're rotating.
Yep.
Yeah, that way. That is wicked
That's
cool.
a surprise quiz.
What
is
right.
the 3D rendering?
Yeah.
Surprise quiz.
And
there's a surprise.
There's a surprise quiz.
Yeah.
People are
I expect Vitor's picture to look this good by hand.
Yes, I'll
All
use
right.
my sheet.
Okay. So please jump on that quiz. It's like some homework problems you saw in section 2 and section 3. And you get to choose disks or shells. My belief is one of them is easier. Unfortunately, you don't know which until you try. All right. So let's see. On number 2, I decided to give you the formula if you want it.
Oh, that's
the formula.
Yeah. So when you set up your arc-like integral, it's going to look something like this. You're going to have an A. Everyone's A might be a little bit different. And then that's the formula. Otherwise, you could just plug this into something like the integral calculator. That's cool on this problem, too. Same thing here. This is a similar problem to the previous one. Notice it's a quadratic function like the previous one was. And I put that formula up there also for you.
Lovely.
One of these is right. The others are not. And number 4, this is the one I want to do. Okay, so we're going to do this one together. This one is doable algebraically. So remember, my advice for this section is you got to come up with the integral for sure. Otherwise, you can't do anything if you don't do that. And you got to draw a picture to do that. Once you get the integral, try doing it without an integral calculator. See if you can come up with an antiderivative. But if it looks like, for example, this one doesn't look like it should be too bad, square root of 1 plus something squared, but it turns out it is. It took me 2 pages to derive that formula.
Ew.
I will demonstrate that derivation next chapter. Okay? So again, come up with your integral. Try, say, have we done something like this before? Do I know a trick to do this? Right? I think, was this the one we tried substitution on the other day and failed twice?
Yeah.
I think it was. And, give it a try and then whip out the integral calculator. Or whip out the integral calculator and see if what it shows looks familiar. Okay? So use that as a productive tool. This one is doable without the integral calculator, so I'm going to attempt to do that with you right now. And I'm going to remind you of the kinds of things that need to end up in your sketch. Step 1, we need a sketch of this function on the integral. And radical functions like this aren't something we draw often. So this might be one where we're probably going to go to the calculator first rather than go straight to it. But just kind of get a picture of this. There's a square root function going on here. And that square root function is cubed. So it's a blend between a cubic and a square root function. Right? Square root functions look something like that. Cubic functions look something like that. Right? So this graph is going to be some blend of those. Which wins the battle in terms of the end shape? Is another matter of analysis. I'm going to go straight here and enter f of x equals, and I forgot my constant. What was it? 3. 3 times x raised to the 3/2 power. So which function seems to have won the battle here in the shape? The cubic won the battle. The square root is controlling some of its behavior, but the cubic kind of won out there. We are integrating this from 0 to 2.
1 to 2.
1 to 2, thank you. Oh yeah, there's a good reason we're not doing 0. That we'll talk about in a minute. Let's see, go away.
Is this number 3?
4.
4.
This is number 4. Yeah, so I'm just going to draw in x equals 1, show one of my boundaries, and x equals 2 is the other one, right? 2, x equals 2 is the other one. All right. And I'm just going to rescale this sucker so it's easier to draw. Okay, so it's got this cubic type shape going up, and then we have these 2 intersection points, which are about what? They are about 3 and 8.5-ish. My function was what? 0, 0, 1, 3, and 2, 8.5-ish. All right. And it's got a little curvature at the bottom. It's not really straight. It's up. All right, so just other identifying features, interesting. I'm going from here to there, and I'm looking for the arc length. So I want to know what that distance is in there. So no revolution here. I just want to figure out what that arc length is. Our formula, remember, for an arc integral of the square root of 1 plus, what am I squaring? Anybody remember?
No, X intercept.
The derivative. It's the derivative. So you can call it dy dx if you want, or you can call it f prime of x, but we end up squaring a chunk of the derivative. And the Pythagorean theorem, this is a curvature version of the Pythagorean theorem. That's basically what it is. All right, so to figure this out, I need to get y prime, I need to square it, and I need to add 1, and then see if I can clean up that square root. So step 1 here, what is y prime? Y prime is going to be 9 halves x to the minus 1. It's going to give me what, 1 half? Yeah. Is that right? What's that? You gotta go. Okay. All right, so that's the derivative. Then we need to square that. What's that going to give me? That's going to give me 81/4 x. Add 1 to that. And I think I'm just going to leave it like that. And step 4, I guess I'm a bit ready to build my integral. So I've got the integral from 1 to 2 of the square root of 1 plus 81/4 x. Is that right?
Yes.
Yeah. We got that right. All right, so this is a relief. There's not an x squared there, which yesterday gave us fits. Okay. And I showed a minute ago it's a pretty complicated antiderivative. I'm thinking a u substitution on this right here. Anybody want to suggest a u? What's that? The whole inside. Yeah, let's go for the whole inside. Hope that works. So we're going to let u equal 1 plus 81/4 x. du would then be 81/4 dx. Which is kind of cool. I have everything but the 81/4. So I just switch that to the other side. So then dx would equal 4/81 du.
Is that a 4 or a u? Over the d1, is that a 4?
What? This is a 4. Oh, it's getting worse.
Why is it 4 equal? Oh, because we're multiplying.
Because I'm ooh, that's not an eraser. It's going to hell here. Okay. So just for our substitution, u is this, which is right there. And then I'm going to replace dx with this stuff right there. Yeah.
So this just uses u substitution because the derivative of x is 1. There's nothing outside.
Yes. All right, so rewriting that. Oh, should we change the boundaries?
No, why
It's not,
would
you
you?
know-
What?
it's not gonna be that bad putting,
Hey, just put it back in.
Yeah.
Yeah, okay. All right, so then we now have the,
You're really winning this, Gary.
the integral, I'm going to ignore the boundaries for a minute, of 4/81, did I put that in the right order?
Yes.
Square root of u. Which is just u to the 1/2, right?
Yes.
So antiderivative is,
U over 1/2.
nope,
No, that's it.
2u to the 3.
getting there. So we add 1 to the power.
No,
So that's going to give us u to the 3/2. Okay. And then we're supposed to divide by 3/2, which is multiplying by 2/3. Yeah, so that's the way I would write it. Okay. And then we got to put our function back in so we can use the boundaries. So I'm going to switch back to red here. So 4/81. I'm going to pull out the 2/3 too, if that's okay. And then inside here, I have 1 plus 81 over 4. Get the order right, Barry. 81 fourths x, and that is to the 3/2 power. And we want to evaluate that from 1 to 2. Yeah, so that one was doable. Sometimes they work. And now we just plug into a calculator to finish that sucker off. So, whip out your calculators. Let's see if we can agree on an answer. I'm going to sneak Desmos over here, leave the whiteboard there for a moment. All right, so my antiderivative function.
Do you want to show it?
I'll show you what I'm doing in a minute.
Okay, I just.
So do you have a calculator out?
Yep.
Excellent. All right, so I'm going to show you my Geogebra now. I pretty much typed exactly what I saw there for my antiderivative. So I'm making a new function called a of x. It's 481, 4 over 81 times 2 over 3 times that 1 plus 81 fourths x to the 2/3. Okay. And now I'm just going to evaluate that at 2 and at 1 and subtract them. And they're probably not going to come out nice numbers, are they? Oh, they actually are going to come. Oh, no, the plus 1 is going to mess stuff up. Yeah. So if I check out what is a of 2, it's not a nice number, yeah. Minus a of 1. So I'm just now using the fundamental theorem on my antiderivative. So I get an arc length of about 5.6-ish. Okay. Yeah, and I was looking at thinking if we take the 3/2 power of 81 fourths, that's kind of nice because the half power means take the square root of 81, which is 9. But we're adding the 1 to it, which messes stuff up. So, oh well.
Plus,
Oh.
have to
I don't know. I'm actually curious about that. I'm going to try a little algebra on that just for fun here.
take everything to third power without square root.
Yeah, so I have, let's say, 1 plus 81 over 4 times 2 raised to the power of 3/2, which gives me 1 plus 81 halves, 3/2. 1 would be 2 halves, so that gives me 83 halves to the power of 3/2. Which basically means take the square root of 83 halves and then cube that, or vice versa, right? And 83 is 83. Is that? I think it's prime. No. Oh yeah. Yeah, I think it's prime. So.
Yeah.
So you're gonna So you're gonna have square roots in the answer. It's not gonna come out to some nice fraction. So, and let's see, what do they want here? Enter a mathematical expression, and it doesn't say no decimals allowed, so I should just be able to type a decimal version. It's a matter of just typing enough decimal places. Where'd Geogebra go? There it is. 5765, maybe? It's close enough. Cool, we got one right. That wasn't too bad.
We do number 7.
We can certainly try. Ooh, yeah, that's a cute one. All right, let's go for it. And we tried a problem like this in class the other day, right? Remember I tried to find the arc length of the sine?
This is what we have to use.
And the integral calculator is like, I don't know an antiderivative for this. So that's likely to happen again. Am I on the right one, Daphne? Is the one you want to know about?
Yes.
Okay. So we have y equals 3 sine of 2x from 0 to pi. And I think I will copy that information into my screen. If I can find my whiteboard tools.
Have we done the surface?
Oh, we haven't done surface area yet.
Oh, maybe that's why.
Okay, let's do surface area. That was my next topic for today anyway.
Gonna say.
All right, so I'm gonna squeeze another slide in back
Just gonna
here.
rotate what we already did.
Yeah, we're just gonna take arc length and rotate it. So I just wanna show you what that looks like.
Sorry, then.
So surface area by rotating an arc. So I have some function f of x, and I got a starting point and an ending point for it. Now we know how to find the arc length. Sometimes that involves numerical calculations because we can't always find an antiderivative, and that's just life. Here, though, we're going to rotate about an axis. So anytime you do a rotational problem, you've got to draw the figure you're working with, and you should always label the axis of rotation. Okay. Other things that need to go in there. Once you draw the function of the axis, you should draw in the radius that is getting rotated. Okay. And then you should draw the thing you're rotating. And for us, arcs are these little diagonals from the Pythagorean theorem. Okay. So remember I called that ds the other day? So if I zoom in on ds, that's ds there. This is dy over there, that's dx right there, and they form the right triangle. So we're rotating that object, and on that object, we only care about that there. We're not rotating in a chunk of area to get volume, we're rotating a segment to get area. We're taking a one-dimensional thing and turning it into a two-dimensional thing. Okay, so what happens when I do that? Well, when I rotate that, I'm going to end up with this thing that looks like that.
Not with that, you're not.
It's not that exact, but it's a general idea.
Big circle, small.
That's super curvy, Gary.
What?
No, but he's rotating.
I'm
the
rotating
other
this
way.
line segment right there.
Yeah.
So that line segment is
It's
right,
in the opposite.
that line segment is right there.
Oh, that.
Oh.
So DS.
So if you rotate that through this radius, you're going to get a chunk of a cone.
Yes, okay.
So we
Okay.
Oh.
So if we
That
write
makes
DS as a
sense
rectangle.
But
So
how do we
ds
know-
is not a rectangle here. ds is a slanted line segment. This is important.
Wait.
I'm not rotating
Oh, we're getting the surface
dx.
area.
I am rotating ds. I'm taking
I
an
see.
arc and I'm rotating that arc. Okay? ds is a chunk of an arc. When you rotate a chunk of an arc, you generate a cone. And what I'm curious about on this cone is not how much water the cone can hold. I'm curious about how much paint I need to cover that outside of the cone. That's what we're calculating here. Okay?
There's my.
So it turns out it's not that bad. So a cone is related to a cylinder, right? It's a cylinder with a slanted edge. No big deal. So for a cylinder, we've done cylinders before, right? Yeah, we did a bunch of them the last few days. Okay. What is important there? Well, oops. You rotated through this radius, true?
Yes.
Okay. When you rotate that, you generate a circle, and a circle has a circumference.
Mhm.
Now on a cone, we would just want the height of the cone to get the outside, a cylinder, we would just want the height of the cylinder.
Mhm.
But here we have a cone, so we want that slant length. Okay? So the things that give me that paint are going to be 2 pi times my radius. That's going to give me my circumference. And then to turn that circumference into a cone, I need that slant length. Well, we calculated that slant length to be the square root of 1 plus the square of what? F prime or dy dx. I'm going to call it dy dx here for fun. Yeah. Okay, what is r in this picture?
The function.
It's the function, yeah. So it turns out we get 2 pi, the function value, right? The distance from here to here is f of x. It's the y value. Times the square root of 1 plus the derivative squared.
Where does ds come in?
Good question. New color. ds is that square root
Because it's
from yesterday's
Because
work.
it's arc.
So that's
Oh,
the
ds is arc.
ds is a chunk of arc. Yeah, and remember we talked about this in class the other day. I can't remember who chose s and y to call arcs s. I don't. Maybe it's a French thing. French dominated math for many years a while ago. Maybe it's a weird British thing. I don't know.
It's not in there.
So
It's not an American thing.
DS makes it slanty, right?
What's that?
DS makes it slanty. That's the thing that makes it.
ds is this chunk of the arc, but straightened out temporarily.
That's why it's.
And if we
so-
make ds small enough, you can't tell the difference between these little tiny segments and the smooth curve.
So it's not.
That's the point of an infinitesimal, yeah. It's like beyond subatomic particles.
Yes.
Is what they are. So here's what we have then. We just took the arc length formula, so I'm just going to remind you what the arc length formula is. Arc length says integrate the square root of 1 plus the derivative of your function squared. Now we have surfaces of rotation. Now this won't find every surface, it's only surfaces you can generate by rotating something. So surface area is kind of a tweaked version of that. It's 2 pi times your function value. That gives you a circumference times your arc, or a little chunk of arc length. So that's surface area right there. Yeah, in some ways it's worse, in some ways it's better.
Looking at it isn't too bad.
Because one problem we had with arc length is when we tried to do a u substitution, the du was nowhere to be found outside. This gives us a hope of finding du sometimes.
Isn't du inside?
You'll see what I mean in a minute.
But du to find d. Wait, d. Wait, never mind.
Just the derivative of the integers. The derivative of f prime was f of x. So that's
So, okay, so now we're going to do Daphne's problem
Number 7.
using number 7 because we needed the surface area formula right there.
Oh, that's always
Okay. So, do I have to draw a sketch to be able to figure out what goes where?
Yes.
Yes, you do. You do. Okay, so here's the surface area problem we're going to try to do. We've got y equals 3 times twice the sine of x on the interval from 0 to 2 pi. So I'm going to attempt to sketch that. So the sine waves starting at the origin and going up and down. The 2x basically shrinks this horizontally. So instead of having a period of 2 pi, it now has a period of pi. Pen freak out there. And blame it on static electricity and the excitement of surfaces. Okay, so pi over 2 happens to be right here in the middle. So what that means is we want to take this arc right there and revolve about the x-axis. So we're going to make a football type shape out of a sine wave, which I'm not going to try to draw. That's okay.
No, here, I want to see your
I
art.
want to see it.
Okay, there it is.
It's in the plan.
Thank you.
All right, so in order to do this, we need to know a couple of things. So remember, label your axis by putting a little rotating arrow about the axis you're working with. Once you get that, draw in the radius that's being rotated. So we're going to have this little chunk of arc here. I'm just going to sketch in as a little diagonal line there. That's going to be spinning around to make this happen. When I do that, that means this is dependent upon x. So this is a dx versus a dy. So that means I want y as a function of x. Okay? Which I have. Okay? F of x right there is 3 times the sine of 2x. All right, we need f prime in our work here. So f prime of x, derivative sign is cosine. Chain rule says multiply by 2. 6 cosine of 2x. And I'm just going to write this sucker out. So our surface area, we call it SA, is going to be the integral as x goes from 0 to pi over 2 of 2 pi times my function, 3 sine of 2x. Uh-oh, I'm running out of room here. I have to... I have to shrink this a little bit. Let's see, can I grab enough of that and slide it over? Yeah. Some extra stuff there. Okay, I think that's enough room. Times the square root of what?
1 plus
6 cosine.
1 plus that thing squared. So 6 squared, I'm going to call that a 36. And then I'm just going to call that cosine squared of 2x. Okay. Eek.
With nothing to do.
Yeah, so let's see. The question is, what should you be here? Define an antiderivative. All right. So what's your first guess at u?
36 cosine 2x, right?
36 cosine squared of 2x?
Yes, that bit.
Okay, we can try that. So if we let u equal 36 cosine squared of 2x, what will du look like? And what we're hoping is that du is going to appear outside of the square root.
Oh.
Because du is related to dx, right? And isn't dx outside the square root? Yeah, that's the point of a substitution. William?
Wouldn't it be better to make it plus 36 cosine?
Might as well do the 1 plus all that. Sure. Let's throw the plus 1 in there. Okay, antiderivative. Well, the 36 is just chilling out. Here I have a function within a function within a function. So the chain rule applies here twice. Okay, so what's the outermost function of the cosine squared of 2x?
Cosine squared.
The square. Okay, derivative of a square is twice the function. Okay,
Oh, yeah.
so that's the derivative of the square. What's the middle function?
The cosine.
Cosine.
So we have to multiply that by the sine of 2x. Oh, negative sine of 2x.
Times 2.
And we need to multiply that by 2. Okay, so what does that give me? And that's a dx. So I get that du is equal to 36 times 2 is 72, times another 2 is 144, make it negative. Negative 144 cosine of 2x, sine of 2x.
Negative sign.
I got the negative right
Negative
there.
outside.
Yeah. Does that appear outside of my square root?
No.
I just have a single sign, right? So this is cool. I see that outside, but that's not there, so this didn't work.
We tried.
That's okay. We did try, right? So scale down from there. Okay. Choosing Vitor's first option of not using the plus 1, that's not going to change anything. So what I would do is ditch the square next.
Just the square.
Yeah, and just take
Yeah, so-
36x
So again, oops, wrong way. So I'm just going to rewrite my integral, and we'll try this again. So I have the integral of 2 pi times 3 sine 2x times the square root, and I'm going to write it as 1 plus parentheses squared. And inside the parentheses is a 6 cosine of 2x, is that right? Which is where the 36 came from. So I'm going to try this time letting u equal 6 cosine of 2x.
Because just have a u squared. That makes sense, yeah.
Yeah, so we're just going to ditch the square because the square turned out to make things worse for me. Maybe this will make things better. I don't know. So du would be, let's see, 6 times 2 or 12. Derivative of the cosine is the negative sine of 2x. Okay, and the constants outside are no big whoop. We can fiddle with those. Yeah, we got my dx. Is there a sign outside there?
Yes.
Ooh, there is totally a sign outside there. There's not a negative 12. There almost is, right? Not quite. So what I'm going to do is I'm going to move the negative 12 to the other side and say I have negative 112 du is equal to the sine of 2x dx. All right, so now substituting in. So let's just double check what's being replaced. U is just that part right there. And du is going to have a little extra stuff, and that's going to replace the sine of 2x dx. And everything else stays. So whenever I do a substitution, I always double check for myself. What is u and what is du? Otherwise, you might miss something.
It's fine, because all that's left is constants.
All right, so let's see. What do we got here? We're going to have a 2 pi. We're going to have a 3. And then this and this are the du.
The negative 1.
So I've got that. I need a negative 1/12, so I'm going to put that in. And then I'm stuck with the square root of 1 plus u squared. And the constants can go outside, so I can put my integral symbol there. So 2 right there, 12, believe it or not. Okay, do we know an antiderivative for 1 plus u squared?
Yes.
Unfortunately, we do. I listed it in problems 2 and 3.
What's a nasty formula?
It's a nasty formula. That's it right there.
Awesome.
And we have our 80.
So u would be that. So instead of so I have an ax here. We would have a u instead of an ax. So everywhere you see an ax, it would just be a u, and you could replace a with 1.
Awesome.
Okay. So
This is like the direct tangent or something like this, except for it's the
arctangent's 1 over that. No, sorry. It's not. That's not even the arctangent. It turns out that's a natural logarithm. We're not going to get to that till next chapter.
Okay.
So it turns out, even though our substitution was kind of effective, it wasn't effective enough. So you don't know until you try. So what do we have to do here? We have to use an integral calculator. Yeah.
How did the people before us figure this out for us?
They did it all by hand before.
Yeah. So when I took calculus, the instructor had this very large book about the size of this book here that was only filled with integral formulas. And you would search through the book looking for something that's kind of like what you were stuck with. Otherwise, you sought out the computer science departments to help you find a numerical answer.
What about the ones that can't be solved?
That's when you would seek out the computer science department, and they would help you write a program to do a Riemann sum to get an approximation.
So we'll have to.
So what had happened before computers? People found ways to do them by hand,
Oh.
and they would spend pages and pages doing hand calculations. Yeah, so 200 years ago, people were trying to do things like this, and they just did tons of numerical by hand calculations.
You guys
They're very
really
smart
like
about
math.
Really good at algebra.
That's all there was. So not only were there tables of formulas like this one right here, there were also books filled with numerical approximations of things. Like, what's the natural log of 3? What's the sine of 1/12? You know, things like that. Seriously, that's the way it was done before calculators. And how did they make those books? Lots of sweat and blood and ink and truly, that's the way it worked.
Where the slide rule came in.
So the slide rule, yeah, the slide rule kind of was in between doing all the numerical calculations by hand, because people found tricks, right? You had to, because otherwise it's too painful to do. And those tricks led to, oh my gosh, we can make a ruler that does this. That does square roots, that does logarithms, yeah. So that's where the slide rule came from. It was like one of the first computers. Really, too, it moved, right? And you could compute stuff. It was a computer. Do you know what a computer was before that? It was a human being who made calculations. There were actually people, that was their title. I am the computer of this organization. I calculate stuff. Yeah, William?
Later on, there were mechanical hand crank calculators.
Yeah, there were mechanical hand crank ones too. Yeah, there were some amazing ones out there that were all gears and stuff.
What would be like an example answer? Would you just be a decimal?
This one right here, yeah, you can come up with an exact answer based on a formula like this, but the exact answer is going to be kind of a mess of stuff. Yeah. So on this one right here, the answer is not expected to be exact. On number 7, the answer is not expected to be exact because the formula is so darn complicated. I could state an exact answer, but it's going to be just the answer would fill up the screen if I wrote it exactly. Right? Think about it. Because we would have to evaluate this formula here, where instead of an AX, I have a U, but what was my U really? It was 6 cosine of 2x. And then I have to throw a 2 pi inside of that.
Yeah.
Yeah, because we were about pi over 2, sorry, because we were going from 0 to pi over 2. And is this going to zero out when the angle is 0?
Probably not.
Maybe, I don't know until I check. So there could be a second part of it that gets subtracted. Okay. All right. So on a test, I will make it clear whether I expect you to be able to do it by hand or whether I expect you to just write me an integral and then plug it into the other calculator. Or Desmos, or Geogebra, whichever one you like.
Or all 3 of them, double check.
All 3 of them double check, yeah. All right, let's set up another one. We got that one set up. That was the hard part. We found U substitution was marginally helpful, but not completely. That was 7, 8. Oh, they even dropped. Ooh, I know what I want to do.
What is that?
Yeah, I know what I want to do here right now. Okay, we're going to do a slightly easier problem.
Are they always positive numbers?
What number is this?
They have to be.
I'm not going to do that one. I'm going to do a different version.
If it's a negative surface area, it doesn't make sense.
So f of x equals 1 over x.
Wait, which one?
This is like problem 8.
Like problem 8.
Yeah.
Number 8.
We are going to do 2 things. We're going to find the arc length as x goes from 1 to 2. And we are also going to find the surface area. Let's see, no. I don't want to do arc length at all. Take that back. I want to do surface area from 1 to 2. And I also want to find the volume from 1 to 2. And to do that, we're going to revolve around the x-axis. Okay, so that's what we're going to try to do here. Oh, really? Let's see what else can stay there. All right, so quick sketch, set up our integrals. So this has a point at 1, 1, and then 2, 1/2. 3 would go with 1/3. So this sucker swoops down and forms an asymptote. So the x-axis, aka y equals 0, is a horizontal asymptote of this function. And we are going to spin about the x-axis. So whenever you do something like this, again, sketch your function out, label with a little rotational arrow what axis you're rotating, draw in some information about what's being rotated. So in this case, for the first part, that would be my radius of rotation, which is just a function value here, over x.
What's M and X?
So some things that we're going to need to know right here for surface area. It's the integral 2 pi times your function, which is your radius, right? Times the square root, your ds, 1 plus f prime squared. So we know here f of x is 1 over x. F prime of x is, no, that would be the antiderivative of 1 over x.
Oh, square. 1 over square.
So this is x to the negative 1. So,
2 over x squared.
yeah, so drop the power, drop it by 1,
And then divide
which
it.
could be 1, negative 1 over x squared is the way you could write it. That would be the derivative here. And then keep in mind, we need to square f prime too. Come on, time? Okay, let me just write this and we'll quit. So then I have the integral of 2 pi times 1 over x times the square root of 1 plus this thing squared, my derivative squared. If I square a negative, I get a positive. If I square x squared, I get x to the 4th. And here I'm going from 1 to 2. Turns out you can clean up that a little bit. Not a lot, but a little bit. All right, so I'm gonna have to stop there. I'll pick up this problem tomorrow. I'm gonna spend one more day. Tomorrow's Tuesday. All right, we gotta wait till Tuesday. You have until Tuesday night to finish this homework, by the way. So what we're gonna do is we're gonna look at an interesting experiment with this on Tuesday. You're gonna generate this cone, right? It turns out you can explore the idea of letting the end boundary of that cone go to infinity. What if we had an infinitely long cone?
Uh-oh.
Oh my goodness.
Is that possible?
Will you have an infinite?
Might it have
surface area?
infinite surface area? Might it have infinite volume? Or could it have finite volume?
If it's an infinite.
Don't some limits as we take them to infinity have finite volumes?
Yeah.
Finite values?
Yeah.
Yeah, sometimes. We go to infinity, it goes to 0 or 2 or 1. Huh, what could happen here?
Oh, boy.
It's pretty cute.
My dad.
Oh.
It was also my dad.